Welcome back to Learn a Lot, and in this video, as part of our series Introducing Proofs Through Worked Examples, we're going to look at a proof by induction. And the statement we're going to prove is that this formula, the sum of all numbers from 1 to n is equal to n times n plus 1 over 2. We're going to prove that this formula works for all natural numbers n. Now here, natural numbers are 1, 2, 3, and so on. They're also referred to as counting numbers. But before we get into the example, let's just briefly go through what is a proof by induction. Proof by induction. So a proof by induction is for a very particular class of statements. It's to prove statements that apply, so for statements that apply for all natural numbers. Or really it's for statements where there's some kind of indexation you can count. There's a n equals 1 statement and a n equals 2 statement. You might start earlier. You could start at an n equals -3 statement, and then you go up -2, -1, 0, 1, 2, 3, so on. Or maybe you start from n equals 6 or n equals 7, and then you prove that it's also true for 8, 9, 10, 11, so on and so forth. So it's for statements where it applies, or the technical term is a countable set, which really has a lot to do with this set of natural numbers. But for now, feel free to think about it as, in some sense, statements which you can count. So here, the way that we can count the example we're going to prove is that you can count n. So n can be 1, 2, 3, 4, so on. And we want to prove that no matter what you pick, the formula still works. The way proof of induction does this, because obviously we're not going to check for every single n, there are infinitely many, so we don't want to have to check all of them, we'd never finish. So how does proof by induction prove it for this infinite number of statements? The key is it uses this kind of domino effect. And this domino effect is laid out in a very specific way. So proof by induction follows a very specific structure. So it'll be good to see this example so that you can see that structure and use it on your own. So the way we set up the domino effect is we prove something which we call a base case. So we prove the base case. And think of this as just the first instance, or the number I start at. So in this case, we're starting at n equals 1. So the base case is the n equals 1 case. But if I start at something like -4, -4 might be my base case. If I start at 12, 12 might be my base case. So the base case is just the first instance of this statement. Then we perform the induction step. And the induction step goes like this. We assume the statement is true for some particular value. It doesn't actually matter which one. We just assume that there is a value which exists where the statement is true. And based on this assumption, we prove that the statement is also true for the next number, k plus 1. And if we combine this layout, we see how we get a domino effect. So if we have a whole bunch of statements which we can count, maybe we lay them out like dominoes. We can count dominoes, so let's just consider our statements as dominoes. We prove the base case, which is the first one. So that one's true. And then we prove that if something is true, then it's going to knock over the next domino and the next domino will be true. So if some statement is true, then the next one is true. And we proved that the first one was true. So that means the next one's true, so the second one's true. But now that means that one's true, which means it's going to knock over the next one. So the third statement's true. And now the third statement's true, so it's going to knock over the next one, the fourth statement. So the fourth statement's true, and it's going to knock over the next one, and so on and so forth. So that's how we get that domino effect. So with that out of the way, let's jump into the example. And remember, proof by induction is written in a fairly particular way. So I'll be paying close attention to that structure with this example. We want to prove that this formula is always true for all natural numbers n. Another way you might write this is n greater than or equal to 1. First, I'm going to say that we prove this by induction, so that my reader knows how I'm going about this proof. They know to look out for the structure, the induction structure. Now, I start with my base case, and I actually write base case, n equals 1. So for the base case, the formula is k equals 1, 1k, which is just equal to the number 1, and that is equal to 2 over 2, which is equal to 1 times 1 plus 1 over 2. And that is in fact this right-hand side of the formula. So the statement is true for n equals 1. Now I perform my induction step, and I actually write induction step. Suppose there exists an m, which is a natural number, such that this statement holds for m. So that's that first part of the domino effect. I'm assuming that there exists some number that it works for. And based on that assumption, I want to show that it also works for the next number. So m plus 1. So I want to show this. So let's show that over the page. So let's start again with that left-hand side. The sum from k equals 1 up to m plus 1. Okay? Now, from the way that summation notation works, this is the same thing as the sum from k equals 1 up to m of k plus that last term, which is just m plus 1. So this is true. And now what I'm going to do is I assumed that the formula worked for this one. I assumed that the formula worked for n equals m. So I'm going to plug in the formula now. So this is equal to m plus 1 over 2 plus that last term, m plus 1. And I'm going to write by the induction hypothesis. So the induction hypothesis is that assumption I made that the statement is true for some value m. So since it's true for some value m by the induction hypothesis, this thing here, I can plug in the formula. So I know that this sum from k equals 1 up to m plus 1 k is equal to m plus 1 over 2 plus m plus 1. And now I'm going to bring those into the same fraction. So I have m plus 1 plus 2, m plus 1, over 2. And if I simplify that fraction I just wrote by factoring out that common m plus 1 term, what I am left with is m plus 1, m plus 2 over 2. And that is what I wanted. So I might write as required. So I've now proven that if it's true for some value m, it is also true for m plus 1. So the last thing I have to write, just so it's really clear to my reader how this proof has gone, I'm going to kind of summarize. I'm going to write, so by the principle of mathematical induction, and then I'll just write what I've proven. This formula, the sum from 1 to n of k is equal to n plus 1 over 2 for all natural numbers n. This formula works for all natural numbers n. So this principle of mathematical induction thing that I wrote, that's the domino effect I was describing earlier. That logical domino effect. How since it's true for n equals 1, it's true for n equals 2, now it's true for n equals 1, it's true for n equals 3, and so on and so on. That's the principle of mathematical induction. And there we go, that's done. That's the proof. And as a little bonus, you get a neat formula out of it. There you go, that formula is true. If you ever want to compute the sum from 1 up to n, just n plus 1 over 2. That's a quick way of calculating that sum. So hopefully you found that helpful and interesting. And with that, I'll leave you to it.